So just imagine, if you want to start a fire in the woods, right? Is it easy to start a fire in the forest? No, right? Generally, it's not so easy, lah. You can't really, like, the inertia is high, like the impedance, right? But when you start a fire, one tree burn out is okay. But you have a cluster of trees burn out, you realize that the fire spread faster. Correct? It will peak what? But then you accelerate, it will burn until like very jialat. But it will not burn forever what? The rate will decrease at some point, right? When there's not many trees left for you to burn. So you get the idea. When you start burning, initially it's very hard to start, but once you start, it just go wild. But then it will taper off. Then after it will start going down. So this is the question. This is how you model it. Give you an idea of how it works. I'm trying to translate what you intuitively already know into mathematics. Okay, so you know that the rate should go up and come down. Okay, that's the thing. So we start in an established forest fires, the proportion of total area of the forest has been destroyed is X. Okay, and the rate of change of X respectively is called the destruction rate. Okay, that's pretty okay. So I'm gonna just draw a plot of land with trees. Okay, maybe not trees lah, but let's say this is being destroyed. Okay, this is destroyed. Destroyed. Is destroyed. And the proportion here is X. Okay. So the not destroyed is what? It's a proportion. It's just 1 minus X. Okay. Proportion means it's 1 minus X. Okay. 1. So this is so dx dt obviously is called the destruction rate. The rate of you destroying the forest is called the destruction rate, which is destruction rate. Okay. Then the next part is what? Okay, great. Investigation shows that the destruction rate is directly proportional to the product of proportion destroyed. Product meaning X, proportion destroyed will be X, and proportion not destroyed is 1 minus X, right? You see that? So destruction rate is proportional to destruction. This one don't really need in and out because it's just we are just examining the destruction rate X times 1 minus X multiplication. Okay, so the destruction rate is this. So dx dt is equals to k x 1 minus x. Now what you understand is this. I want you to make sense of this. So if you are, what graph is this? This is actually a quadratic curve. Right? You start off with 0 here. You end with 1 here. So at some point, blazing fire, you shoot up here. Then you go up, wildfire. Then you taper off. Okay, so this is how you should appreciate math. Should. You realize that the rate of increase is maximum here. The rate of increase is max here. Like around here, where this is the steepest slope. The steepest slope shouldn't be here. The steepest slope should be here, around here. It's the fastest at the start. Okay, the rate of increase. So that's how you the forest. Then after it start to taper off like that, and then it start to decrease here. Okay, that's it. Oh, no wonder the next one is the interesting bit. Okay, I will stop here and you try. Okay, let's look at the next one. If a particular fire is initially noticed, so when T, I'm not sure, T is 0, okay, T is 0, when one half of the forest is destroyed, so when X is equal to half, right? Half is already destroyed. Now it's found that the destruction rate at this time, at this instant, such that if it remains consistent thereafter, the forest will be completely destroyed in further 24 hours. This one is a bit jalat. This one is quite jalat. One half of the forest is destroyed. Okay. So I repeat. So it say, okay, we use circle. Circle is the easiest to understand half. So when you talk about already half of it destroyed, X is half. Then a non-destroyer is half. You take 24 hours to burn this. At this juncture, if the rate is held constant, we know that the rate will not be held constant. But if it is held constant, you will require another 24 hours to burn it. All right, I repeat. We know that the rate is not held constant. Obviously, it's not held constant. Okay, but if it is held constant, hypothetically, it will take 24 hours to burn. Okay, that is what they are trying to say. Chim, right? Not chim lah. It's just very confusing. It throws you off because that is what they are trying to say. So what I'm saying is, at that rate, so hence, the constant rate they are looking at, the constant rate, at this instant, the rate should be half divided by 24. Any issue? Right? This is the constant rate you're looking at. If it's half constant, this would be the rate. Correct? So that is your boundary condition. So let me just okay, question please ask. I know this part is a bit confusing already, so I need you to stick with me. So when x equals to half, we know that dx dt is half divided by 24 if held constant. Yeah. So hence, you can actually, this is a boundary condition. This boundary condition is more chalat, the worst that you could. You realize the question arranged in a way that I'm showing you a different type of boundary condition throughout. So for previous one is when it's held constant, like this kind when it's held constant, okay, dxdt net is 0. Then this kind when this no trace of drop, this is the easiest lah. This one no trace of drop, t0, x0. See all these boundary conditions, the worst is the one with the red one, okay. The boundary conditions are the conditions which you use to solve for unknowns. So just so you know, this part here, sub back into this equation. So sub into 1. Is it okay? It's a direct proportion, so this is just direct proportion. This would be great. Subsequent is just solving, so I don't think it's like by parts and so on. I think this is all okay. If you're struggling here, you really need to practice your techniques. There's nothing DE here. It's all solving. Aiyo. Seven three one 731.73105. So X is proportion, so actually the forest. Okay. Yay, forest fire.